Cool, excellent. Well, thank you very much for inviting me to talk today. So I'm going to talk today about a small collaboration we did with Creative Analytical through the Analysis for Innovators scheme. Basically doing trying to develop a data algorithm for combined XPS and HAXPES spectra. So there we go. So XPS is great. It's very highly sensitive, which is great when the thing you're interested in that first top 10 nanometers, for example. But if you're dealing with stuff which is you're looking at buried interfaces or things that are underneath your surface, you want to get to the subsurface, then it's not so great. And that perhaps we can then go up to using HAXPES. But again, if you're having to go deeper again, then you may have to resort to removing surface layers to obtain more accurate information about the subsurface material. So you really depth profiling, which is fine. I mean, there are lots of studies on depth profiling various materials, organics, for example. There's plenty of work in that field. But for other materials such as inorganics, you can have issues where sputtering does not help because it can result in sputter damage to the material. So as you're etching down through your materials, try and reach the depths of interest, what you're left with is a small altered layer of the surface, which then XPS gives you a false quantification from your data. And that can end up dominating the XPS signal because it's at that surface. So that was the question that was kind of brought to us by Kratos. We were trying to think, is there a way that we can use the combined aluminium and silver source on the super to try and find an analytical way of removing that altered layer? And so we want to try and exploit the fact that we've got two sources here which generate photoelectrons with differing information depths. So HAXPES has, higher energy means that we're getting a larger kind of effective attenuation length. That means that the information depth is greater. So that's what's kind of represented by that top graph there. We can see that if you normalize the surface intensity, you can see that there is more information that goes deeper into the sample for the silver source compared to the aluminium source. And what's important then, what that shows is that the HAXPES data there contains the XPS information. So we can remove that XPS information, and what we're left with is a surface-free depth distribution, and that's what's represented by that bottom curve. So that bottom curve is firstly absent of surface information. There is no intensity at the very surface, the vacuum surface interface. It's dominated by the subsurface. When you compare this to the normal spectra, the surface is the dominant intensity. But in the surface-free depth distribution, it's typically it's dominated by the subsurface instead. And finally, the information depth is actually greater in this case because in the silver source and the aluminium K alpha source as well, the mean depth of intensity is coming from is basically about one attenuation length down into your material, whereas with the subsurface, the surface-free depth distribution is effectively a sum of those two effective attenuation lengths. So, sorry, going back to this. So really, we want to get to a situation where in that top graph, we want to make sure that our surface intensity equals in some case. So but to do that, you have to know some scaling parameter. You need to know something that you can multiply the intensity of the silver spectra by in order to match the surface intensities. Okay, and that's not quite so simple. If we can do that, it means that we can then, as I said, subtract that XPS information. What this looks like from this is not sort of real data. This is just some simulated data we put together. But basically, let's assume a situation here where we sputtered our material. We had a pristine material initially. We sputtered it. We then altered the surface layer, and so we have, for example, two components where one would be the undamaged subsurface material, And then we have another component, which is the altered layer. Now, obviously, because of the different information depths, the aluminium K alpha source will have a higher proportion of the damage in the spectrum compared to the compared to the silver source. So in this situation, we've got the middle spectrum there has been multiplied by some scaling factor in order to match the surface altered layer intensities. And that means then when you subtract the aluminium K alpha information away from the scaled silver L alpha information, your altered layer component is reduced or completely removed. And so you're just left with the subsurface information. So that's kind of represented. We've also kind of tried to represent that as well with a simulated system here where you've got some material which was some dioxide, and then the altered layer is you're basically removing oxygen. And you can see that as that altered layer thickness increases, we get initially a very, very thin layer thicknesses. So we're talking 1 to 2 to 3 sort of nanometers. It does a pretty good job of removing that altered layer almost completely. Of course, as that altered layer thickness increases, then that's the limitation of the algorithm. We start to not be able to remove that altered layer in the data, but we are reducing its contribution to the spectrum. So the question is, how do we find that scaling parameter? Now, it should actually be fairly straightforward. Really, it's just a ratio of the sort of theoretical and experimental factors that would contribute to that total photoelectron intensity. So, we can go find those values in databases and literature, but getting the right combinations of them in order to get the correct scaling factor is actually quite difficult to do. It's difficult to predict, basically. So actually, the easiest thing to do is to just measure your material. So measure a homogeneous material containing whatever element of interest you have, and from that you can then calculate your scaling factor. And that's what's represented by that top equation there. It's the intensities there of a particular core level in the homogeneous material for both the aluminium K alpha and the silver L alpha, multiplied by the reciprocal in this case of the effective attenuation lengths. And that's basically how you get your empirical sensitivity factor. And that's a lot more, that seems to work a lot better than just trying to predict it from theory. And it's probably easy to implement for any user, basically. We also worked out that you can, if you've got the scaling parameter, it's in a situation here where maybe your starting material before you've started already has some inhomogeneity in it. Maybe it's got a thin film at the surface or surface contamination or something like that. In that case, you don't have a homogeneous material to measure from for that material. So what you can do is measure a different homogeneous material. For example, we used silver foil, for example, sputter cleaned. And then you can use that to convert from one scaling factor on one material of a particular core level to a different material on a different core level. So I'll give a few examples. So silicon wafer, this is with a native oxide. This probably gave, I think, the best example of the algorithm working. It's a very thin film, it's only 1 nanometer. We sputter cleaned, obviously, as I mentioned before, we've got a thin film oxide. We haven't got homogeneous material to start with here. So we measured a piece of sputter cleaned silver. We determined a scaling factor for silver 3D. And then that was converted into the scaling factor for silicon 2P. So here's kind of this is the most clear example, I think, of, that's the wrong button. On the top sort of left spectra, that's the raw spectra that comes out of the spectrometer. So you can see there that the aluminium K alpha data is nice and clear, good count rate, good signal to noise. And then there's a tiny, tiny line at the bottom there. You can barely see it. That's the silver spectrum. That's obviously because the silver alpha spectra, or the photon flux from the silver anode is hundreds of it's a factor of hundreds less than the aluminium. And so that's why you need to apply that scaling factor, is to get is to basically increase that that silver intensity. If you normalize the spectra, then you can see the difference in the depth distribution. So we can see that the silicon oxide component is more intense in the aluminium spectra compared to silver, and that's because the XPS is more surface sensitive in this case. Once we apply this into our algorithm, what we end up here is with the scaled, we have a scaled silver spectrum with a unscaled aluminium spectrum. When you subtract one from the other, you can see that the oxide component is virtually eliminated, completely removed. And that has an effect on the quantification. So whereas before, looking at just the silver 2p, we would get like roughly 70%, 20%, sorry. And then for the silver alpha, we get slightly more, 80%. And then once we've done the removal of the oxide layer through the algorithm, we then get about 96% silicon. So that's compared to the oxygen. So that kind of shows this is like a kind of best case scenario of it working quite well. We tried other materials because really we'd be interested to see if this works for a variety of materials for things like the sort of semiconductor industry or industries which kind of are worried about these altered layers when they're doing depth profiling. We looked at molybdenum disulfide as well. In this situation, very clean, we were able to take a scaling factor directly from the material of interest. We then sputtered this material using clusters. So we were using 10 keV, argon 1000. This happened to be this is only like 10 EV per atom. It's quite gentle. So we don't actually see that much damage occurring. You can really just about see it on the lower binding energy side here at the peaks. But it is still there. And by applying the algorithm, we do remove it. You do see there's a drop in the intensity in that damage. So that kind of showed to us that the algorithm was kind of working as intended and was removing that altered layer. Now, we went up to higher energies per atom for the cluster, so 20 keV 500 now. In this situation, the sputtering was so intense that it was basically increasing that altered layer thickness with time. And so it gets to the point where you're not really removing that altered layer, you're just reducing its contribution to the quantification. That's most clear by the 60-second sputter in the middle there, where you can see the damage component, which is this low binding energy component, is quite significant in both the aluminium and the silver data, but it's the less dominant component in the surface free depth distribution. Of course, at some point, as you keep sputtering, it stops kind of. You're basically reaching a point where you're sputtering so much, and that the altered layers increase so much that there's no real difference in the depth distribution for both those spectra. So what that looks like in terms of quantification. In both cases, that brings the expected stoichiometry closer to the expected value. So it should be 2:1 sulfur to molybdenum. And in both those cases, that did work. It did bring it closer to that point, but didn't get there completely. So really the lesson here is still that you still have to have a quite careful choice in your sputtering conditions. You still need to optimize your sputtering conditions to reduce that altered layer as much as possible before reapplying this algorithm. And then the final kind of, this was the example where it didn't really work much at all. And this was because really this is for titanium oxide. And the problem here is that the moment you start sputtering, it damages so readily that you're basically damaging beyond the information depth of both the XPS and the HAXPES. And so when you apply the algorithm, you actually don't see much difference between the surface-free depth distribution and the two raw spectra. So in that case, no change in stoichiometry and no benefit to using it in the situation. So certain materials may not work on. That's just cruel reality, unfortunately. So just to conclude, this is just an example where XPS and HAXPES data can be sort of combined and used together to we can treat the data in such a way as where we can remove the surface altered the altered layer of the surface using a simple algorithm. This can be used in the case here. It can be used to remove the contribution from things like sputtering damage. It can also work for thin films, the oxide films, for example, or potentially things like carbon contamination. But at the end of the day, to obtain a good quantification after sputtering, we still need to be careful of the sputtering conditions that we're using. So still some considerations to use there. So this was a project that was run through the Analysis of Innovators scheme. That was mentioned at the beginning of this day, where Royce is also a partner of this scheme as well as MPL. It's open to SMEs in the UK who have a measurement problem, which is stopping a product getting to market, for example. So if that's something that you're interested in, there's a measurement problem you want to talk to us about, or then that scheme is still open. I think we've just done the brokerage for round 14, so round 15 hasn't been announced yet. But again, if you go to that website, you can get some information there and make sure you're aware of it when it happens. And also, I just want to thank David and Katerina for their comments, as well as Chris Blomfeld from Kratos as well. We worked very closely with John during this project, basically collecting data on both the Apps Lab instrument at Kratos, but also at MPL. And so thanks very much for your help as well, John. And that's everything. Thank you.